Hello everyone. In this video we'll be looking into the signals in the Linux kernel. We will be looking into a little bit into the introduction, then different sources of the signals and different types, asynchronous and synchronous, and then we will also look into the generation and delivery for both of those types. So this is part one of the video where we'll be covering till the generation of asynchronous signal, and in the second part we will cover the generation of synchronous signal as well as delivery of both asynchronous and synchronous signals. So let's dive right in. So a signal is one of the simpler and basic forms of inter-process communication, right? It is there with a precise goal. A signal is sent to a process or a group of processes, notifying about an event and to instruct or force it to take a specific action. Right, these actions can be default actions for specific signals or custom ones which do user-defined tasks. Every signal in the kernel is assigned a unique numerical value. This numerical value is used to identify the signal. These values might be different for different architectures, as some signals and numerical values are you can look at them by just typing the command kill -l in your terminal in the Linux machine. Uh, in general, the events that generate signals fall into three major categories, right? Errors, external events, and explicit requests, right? So an error means that a program has done something invalid and cannot continue execution. But not all kind of errors generate signals. For example, if you try to open a non-existent file, which is an error but does not raise a signal, instead it just returns -1. The open call would return -1. In general, errors that are necessarily associated with certain library functions are reported by returning a value. The errors which raise signals are those which can happen anywhere in the program, not just in library functions. These include division by zero, invalid memory addresses which would result in a segmentation fault. Right, so another source of signal is an external event. It generally has to do with an IO or other processes. These include the arrival of an input, the expiration of a timer, etc. Right, so the third type is an explicit request. Means the use of library functions such as a kill system call, whose purpose is to specifically to generate a signal. Right, next we'll look at two different types of signals, synchronous and asynchronous. Right, a synchronous signal pertains to a specific action in the program and is delivered during that action. Most errors generate signals synchronously, and so do explicit requests by a process to generate a signal for that same process. On some machines, certain kind of hardware errors that are not reported completely synchronously but may arrive a few instructions later. Right, so synchronous signals are the ones which are generated, delivered, and handled at the same time. This is in contrast with asynchronous signals, which are generated by events outside the control of a process that receives them. These signals arrive at unpredictable times during execution, and they are generated and sent at the same time. It arrives at the process at the same time, but they are later delivered and handled during certain events. We will look into more detail what these events are for both of these two different types of signals in detail, but this is just to give an idea what the two different types are and what are the major differences between them. So let's start with asynchronous signals, and to start with the generation and delivery, we'll typically look into the kill system call, which is one of the ways to send a synchronous signal to another process. Right, and this is how what the definition of the kill system call is. You send a PID to it, which is a process ID to which you want to send the signal, and the signal descriptor number in those two parameters. Now, the PID that you send to it can be interpreted in different ways, right? There are the number of ways that it can be interpreted. If it's a positive number, that means then the signal is sent to the process with the ID specified by the number. If it is equal to 0, then it is sent to every process in the process group of the calling process. So you're basically sending to all the processes of your own group, whoever's calling the kill system call. If it is equal to -1, then the signal is sent to every process. And there are a few more options. Let's just jump away from those. We'll see it in detail when we look into the code. There's one special one. If the signal is sent to is 0, then no signal is sent, but existence and permission checks are still performed. And so this last one can be used to basically check for the existence of a process ID, a process group ID that the call is permitted to send signal to. It's more like a dry run that you do without basically executing the handler for that signal. So these are the ways the interpretation of the PID can be done, and we will look into this detail when we look into the code. Alright, so let's start with the code now. So the kill system call starts with this following function. This is syscall define macro, and you can see the first thing that it does is it calls this prepare kill sig info, which basically prepares this info structure, kernel underscore sig info, and then it passes that structure to the next function, which is kill something info. So let's stop for a moment and look into this kernel sig infrastructure to get a little more understanding. And these are the definition. It starts with a macro, and later in the end it has these 4 member variables. The first is sig number, which stores the signal number. Second is the error number, which basically tracks the error number if it has any error has occurred during the processing of that signal. And third is a code which stores some relevant information. For example, whether the signal was generated by a user land process, it will be like an SI user, or if it has been generated by a kernel process, maybe a trap or an error, then it will be something like SI underscore kernel. We look at this a little more next as we move in the video further. Right, let's now look into how the SIG infrastructure is prepared, and this is the code. It's very simple. It basically clears the infrastructure to 0 and then puts the values that has been sent to it. You can see that sig number sig, error number 0 because it just started processing without any errors, and SI code is basically SI underscore user because right now we're looking at the kill system call, which mostly has been called by user land processes. The next one is the PID, which is set by calling this function task tgid_vnr. This function finds the thread group ID of the current process in the virtual namespace of the process itself, hence that VNR suffix in the end. To understand why thread group ID is being used here, let's take a small detour and understand a little bit about the process and thread IDs, and so that we know what's happening here. So in the kernel, each thread has its own ID, right? It's called a PID, or although it would possibly make more sense for us to call it TID or a thread ID. And they also have something called a GID, which is thread group ID, which is the PID of the first thread that was created when the process was created, right? So when a new process is created, it appears as a thread where both the PID and TGID are the same. When a thread starts another thread, that new thread gets its own PID, right? So this is there so the scheduler can schedule it independently, but it inherits the TGID from the original thread. That way the kernel can happily schedule threads independent of what process they belong to, while processes which thread group ID are reported to you. So if that is why there is a different view by the user and a different view by the kernel. To see this a little bit more graphically, I have taken this from the Stack Overflow question answer, and let's suppose a process in the middle which has PID and TGID as 42. If it creates a new thread, which is on the right hand side, you will see that that process's PID would be 44, because it's basically a new thread which is basically a TID, but the TGID would still be 42. Right, so for this one, if you see the user view, the user would basically see the process in the middle and on the right having both PID 42, because these are basically threads of the same process, but the kernel would look at it differently, and the middle one, it would look at it as PID 42, and on the right one it will look as PID 44, so they can be scheduled independently, right? It's different for a fork. If the middle process forks a process, which is we see on the left side, both the PID and TGID is completely unique and an unused number, right? That's why we are using TGID for the previously allocating as IPID, because we want to be able to send signal to any of the thread for the process we want to send the signal to. Alright, so here we end our detour to we understood what the difference is and why we're using TGID in the previous code. Now we move to back to the signal generation, and if you remember, after we were talking about signal structure preparation, and right after that the function was calling kill underscore sig something underscore info, and this function basically has three major branches, and it is depending on the PID sent to the kill system call. And when we look into this detail, these three branches basically correspond to the different interpretation of the PID that we saw when we were discussing the kill system call previously. Right, so these are the major branches here. We'll look at it in code just to make it clear. We'll just see it a little more simply here. So when the first one is when PID is equal to 0, or the second one is when PID is not equal to -1, which basically indirectly computes to PID being equal to 0 or less than -1, and then the last one is when PID is equal to -1. Right, so let's look at them one by one in code. So this is the first case, as I mentioned, when PID is greater than 0. Right, this is for the case when the positive number, which is PID, is the number of the process whom you want to send the signal to. Right, and in this case, this kill underscore proc underscore info basically calls kill underscore PID underscore info, and it does this in an RCU read log, and that function basically calls this group underscore send underscore sig underscore info. And this is where we stop here, because what we'll find out later is that this function is common for all the three cases. All the three cases, they start with different functions but end up in the same function, and function will further complete the processing of the signal. And we will stop here, look at the other two cases, and then come back to this group send sig info structure to see how it's processed for all three. So the second case, there were two things that are being covered when the PID is equal to 0. That means the signal is sent to every process in the process group of the calling process, the process which was calling the system kill system call. And the next thing that is covered in the second case is when PID is less than -1. Then how it is interpreted is a signal is sent to every process in the process group whose ID is -PID. Right, so both of them is covered by this second case branch, and the function that is used for that is this underscore underscore kill underscore p group info, and that goes ahead and calls the same function that we just saw, which is group underscore send sig info, and it does it inside the loop basically to iterate over all the processes in the process group that it has been chosen, because that's what these two cases represent. That the signal would be sent to the processes in the process group, either of the calling process, or whether if it's in the negative, then it would be if -PID. Right, so the third case is the last one, when PID is equal to -1. So this is a special case because signal is sent to basically every process for which the calling process has permission to send the signal. Right, so it will basically iterate for each process that is running in the system, and then see the process, whether that process the calling process has permission to send the signal to that process or not, and then does it. Thus call the same function, which is group underscore send sig info. Right, so let's recap all the three parts that we took. We started with PID equals to greater than 0, which was kill proc info, again landing in the same function. The middle one was when it's equal to 0 or less than -1, which was basically sending to all the process in the process group, uh, again landing in the same function. The last one was equals to -1. Right, then now let's dive into the common function that we saw that all the three branches landed into, group underscore send underscore siginfo. So the first thing this function does is it checks permission of the calling process, right? It checks permission, validity, security, hooks, everything. So in this, multiple things are checked. For example, whether the signal sent is valid or not, whether the calling process has the permission to send the signal or not, or it also checks some security module, whether if the signal is blocking or not, like SE Linux. And if all the permissions are fine, then the function do underscore send underscore siginfo is called, which then calls this function send signal locked. Right, so the function send signal lock checks whether the signal has been generated by the kernel or not, and this happens if the siginfo structure is set to send sigpriv, right? Or if the SI code, as I mentioned before, is set to SI underscore kernel. It also checks if the signal is generated by an ancestor or not. In this case, one of the ways this is signified is when siginfo structure is set to send sig no info. In both the above cases, whether it's being sent by the kernel or by the ancestor, the force option is set. This option is later used during the preparation of the signal. So after this, the next function that is called is this underscore underscore send signal locked, and it does few major things here. One of them is preparation of the signal through the function prepare signal, and then it does an allocation of the signal queue structure, which is of type struct sigq, and this is how the structure looks. The above structure is basically allocated from a cache, kmem cache, which is named sigq underscore cache p. And if we look into the structure members a little bit, the first one is a list, which is basically used to add this structure into the task pending queue of the process. And if you see, the third one is the siginfo structure, which had been prepared way back, and we have been carrying this all along, and then this is where this is updated. Alright, moving along, we look into this prepare signal function. So the first thing this function does is checks if the process for which the signal is meant for is in middle of dying or not. If so, then it just drops the signal, right? And the next thing that as I was saying, next thing it does is a sort of a job control, and it does it for uh, two of the signals that are related to this is sigstop and sigcount, right? So one of the things, if you are a terminal user, you would know that, let's suppose you're running a process or you're basically open a file in the editor, you can use this shortcut called Control Z to basically come out and put that process in sleep in the background, right? And if you want to basically come back, bring the process and start running it again, if you want it to start running in the foreground, you use FG. If you want to start it running at the background, you do BG. And basically what these two things are doing is, when you do Control Z, it's basically sending a sig stop signal, and when you do FG or BG, it is basically sending a sig count signal. Right, so this is the place where these signals are handled. So basically for sigstop, uh, when a sigstop or sig STP is sent to a process, the usual behavior is to pause that process in its current state. The process will only resume execution if it is sent the sig count signal, and these two basically pair up into a sort of a job control. Another thing to note here is, when a sig stop is to be delivered to a process, if there are pending sig count signal for that process, those are removed. Alternately, if a sig count process is to be delivered through the process, any pending sig stop signal is also dropped. So additionally, for SIGCON signal, the next thing here that is done is that the process is also woken up because it needs to be continued. So technically, if the signal was a SIGCON, the work is done, right? So since we woke up the process, we cleared all the 6 stop signals that if there were any waiting, hence the function returns from here for the specific signal, right? In some cases, the function continues. For example, if the process is being p-traced or not, if there are some more cases, but generally if the special cases are not met, then the function returns from here and the signal processing is done. Right, so we are done with prepare signal. Now next is we have to next what the function does is basically populating the fields of the SIG structure that we just allocated, and add that structure to the task pending structure that I just mentioned, right? And this is the code here that does. So you have the queue here. First, that queue list is basically used to add it to the tasks pending list here, pending list of signals, and all the relevant information is basically updated here. You can see the signal 0 SI user because it's from a system, kill system call, and other details. So with the above steps, the signal is technically delivered to the process because you've added that queue structure to the pending list of the task. Next, the code tries to see if it can find a thread from the process group which can take the signal and wake it up or kick it to the kernel mode so it can process the signal. Right, and this happens in the function complete signal. And this basically is the last major function in the asynchronous signal delivery. So it first tries to find a thread wanting to take the signal, right? And this process of trying to find a thread is done through a function called wants underscore signal. And it checks a number of things. This function, for example, it checks if the thread is blocking the signal or not, and different kind of things, other things. And if, let's suppose, it's able to find a thread which is able to take the signal, well and good. If not, then basically the signal is kept in the shared queue of the task, and any one of the threads can pick it up when it's possible. Right, once all of this is done, the function goes ahead and sets this flag tiff underscore sig pending, and basically kicks the process. And this flag is important because it basically sets sort of a notification saying that one or more signal is pending for the task. And we will see later when the signal is to be handled, delivered. This flag would be checked later in the next video. We will see the other part. And this is where we stop here. We will have in the next video we will start with synchronous signal generation, and then we will talk about delivery and handling of both asynchronous and synchronous signals, because they start at different parts but basically merge into the same functions and handled in the same way. So this is us. We are a small non-profit organization based on basically focusing on disseminating knowledge. Right now we're doing Linux kernel. Maybe we will do other things in the future. You can email us if you want to have any questions, if you want to have a conversation. This is our LinkedIn page. Obviously, this is our YouTube channel. Subscribe and share it. And there will be a blog coming soon with all the more with the text versions of the video that we've been recording, with the notes, with the code bits and everything. So follow us on LinkedIn for news about that. Thank you.